All right. Welcome, everybody, to today's seminar. Our talk today is by Shankar Venkataramani, and he will talk on branch points and C11 pseudospherical immersions. Please go ahead.
Thank you, Armin, and thanks to the organizers for giving me this opportunity to talk about some recent work with Toby Shearman. And thank you all for showing up. This is the summer, and it's a nice day out here. So thanks again for taking time from your day to listen to this. So I'll present sort of the math motivation in a way. This is what I'm going to say at the beginning is just a conjecture, and then I'll build toward what we know about this conjecture. So the question we are interested in is about isometrically immersing, say, the pseudospheres or constant negative curvature into 3 space. And Hilbert showed in 1901 already that there is no complete analytic surface with constant negative curvature in R3. And this has been improved since the time. A particularly nice statement is this one due to Efimov from 1968, where he shows the same result, except with slightly weakened hypothesis. You only need C2 smoothness. And you don't need a constant negative curvature. You just need curvature that's uniformly bounded away from 0 and negative. So that's Efimov's theorem. The counterpoint is a Nash's result that if you're looking in the class C1, then there certainly exists all kinds of isometries. You can have a complete surface with constant negative curvature or any curvature, or even any metric at all, C0 close to any other. So you can approximate short immersions by isometries of or C1 isometries for any Riemannian manifold. So a natural question that many people have looked at is, of course, what happens between C1 and C2. And these results, or the problems I'll talk about, are a little bit in this direction. And so let me just present the conjecture. Right? So Hilbert's theorem or Efimov's theorem, they're about the complete hyperbolic plane. For applications, we might care about finite size domains. Okay? So the question is there a quantitative version of these statements? And in particular, how do these quantitative bounds depend on the class of smoothness? So BR, I'll denote the ball of radius R in the hyperbolic plane. And this is going to be isometrically immersed into R3, or the Euclidean 3 space. Then I will look at immersions in 2 classes. One is C2 and the other is C11. So C11 and C2, it seems like the gap is really small. There really shouldn't be a gap. But this is a statement. Okay? The energy or the object that I'm measuring how nice or how bad a particular isometric immersion is the maximum of its mean curvature, because the product of the principal curvatures is -1. This is, if you want, equivalent to the maximum principal curvature on this immersed surface. And the statement is that the log of this quantity, it grows with R, which is again reasonable, because in some sense, as R goes to infinity, there shouldn't be a finite bound. That's what these various theorems are saying. So the log of the max mean curvature on your domain optimized over all isometric immersions of a certain class. If the class is C2, it grows with the radius. And if the class is C11, it only grows as the square root of the radius. So there's this gap between C11 and C2 isometric immersions. At least that's what this conjecture is saying. And the question is, can we understand this? Why would we even think that there should be a gap? And also, these things seems to have consequences to these mechanics of these objects. And so that's where I'll start. So this is, in a way, the big question, and something that I won't get to prove, but maybe I'll show you some progress about this thing. Please do stop me, ask questions. It's certainly much easier to have a conversation than to have a monologue. So please do stop me and ask questions. So this is roughly the plan of my talk. The first part, I'll talk about isometries of hyperbolic surfaces, with constant negative curvature, and the notion of a topological defect in these things. So that's the first part. And the second part will be to try and put this in a slightly more general perspective that also connects it with the solutions of hyperbolic Monge-Ampere equations, not specifically just surfaces of constant negative curvature, and something about the geometry of the characteristic curves of the system. Okay? And this turns out to relate to Lorentz surfaces and a different kind of uniformization. So I'll put that within quotes. And then the last part will be about the ideas toward the proof of this conjecture, and also about how these things manifest themselves in things that physicists or other people care about. Most of the math work is in this paper, Shearman and Venkataramani, that just came out earlier this year. There's also a physics paper. This is with a bunch of my students, where we talk about the physics aspects of this one. So this is the first part. Any questions about anything so far? I guess I have not said much. Okay. So this is what motivates our interest in this problem. So these are various natural surfaces. There's leaves, there are flowers, there are marine invertebrates, and you see this characteristic shape of there's for lack of a better word, I'll call it a ruffle. And then there can be ruffles on top of ruffles and ruffles on top of ruffles on top of ruffles. So why is this shape so prevalent in nature? And that, of course, there might be many answers. It's good to maximize the area with respect to your radius, because this is good for feeding, this is good for nutrients, or it's good for various other things. So I don't mean why in the sense of what is this useful for, but in a more mechanical or mechanistic or sort of algorithmic sense, how does the mechanics of the surface give it this shape? Okay? So why? Where do these things come from? And it's surprising maybe, but we can actually, I think, say something useful about this. Okay? So these are thin objects, and the physics of thin sheets is just these few simple principles. If you take a sheet of paper, it's very easy to bend it. So this is just a sheet of paper over an edge, and it falls on gravity. It's very hard to stretch a sheet of paper, and this is also true for thin sheets. It's much harder to stretch them compared to bending them. But there is a geometric frustration or a rigidity, namely the bending and stretching are dependent. Okay? So if I take the same sheet of paper and put one stack above but two stacks below, I introduce a weak curvature across the sheet in this direction, that then makes it rigid in the transverse direction. We all know that this is how we eat pizza. You fold it one way so that it doesn't fall in the other way. Okay? So stretching and bending are not independent. How does one put this in an energetic framework? Again, this is very schematic. we have some reference configuration. This is like your sheet of paper. It's a Riemannian two manifold. It has a metric G. You're trying to immerse it into R3, and you want to penalize stretching. You also want to penalize bending. So the stretching is, of course, measured by the difference between the induced metric from the immersion in R3 and whatever the intrinsic metric is. So I'm going to take some matrix norm squared and integrate that. The bending is related now to the second derivatives of this immersion. And so the extrinsic curvatures are given by the projection in the normal direction of the matrix of second derivatives. I'm going to penalize that as well, but with a small parameter epsilon. And the small parameter epsilon now reflects the fact that it's easy to bend compared to stretch. And a way to look at this would be to take the limit as epsilon goes to 0 in some variational sense. Okay? So this is what I just said. And if you work this out for particular models of the material, you get something where this is a quadratic form of the strain matrix. This difference is called the strain matrix, and something that relates to the Wilmore energy for the bending. The integral of the Gauss curvature K is, of course, an invariant if you have a object without boundary. If you have with boundary, it still doesn't contribute to the Euler-Lagrange equations. Anyway, so the point here is you want to minimize the integral of H squared. And Reza, who's here, hi Reza, and Marta. So there's a lot of work in this direction, but in particular, we are interested in the scaling where the energy scales as the bending coefficient. Okay? So there's work in different regimes, work where the energy scales t to a power greater than 2, or even some work where t is between 0 and 2. Here, we are interested in the regime t squared. And so the gamma limit statement is that if the limit mapping phi is a W2 to isometry, then this term is exactly 0, and you get just the integral of the bending energy. Or if there are no such W2 to isometries, then the infimum on this scale is infinity. Okay, so this is, in a way, checking whether or not there are W2 to isometries. If there are W2 to isometries, your minimizers will converge to something that minimizes the bending energy over these isometries, and otherwise, on this scale, you're going to get plus. So that motivates then the geometric problem of trying to find W2 to isometry. Okay? So again, a quick recap again just to set my notation. Here's my reference configuration. Here's the immersion. I've gone from phi to R now. There's an associated Gauss map. If this object is smooth enough, you can define a normal at each point that then defines a mapping from your reference configuration to the unit sphere. The first fundamental form is, it's a symmetric form, and it's dr.dr, where this dot is the inner product in R3. And the second fundamental form is minus dr.dn. So the tangent plane at this point is also tangent to the normal. So they are parallel planes in R3 if you want. So all of this makes sense. This is a matrix that's defined for vectors in the tangent plane. Okay. So that's my notation. And here is the fundamental result is that if the induced first fundamental form is your metric G that you want, so if there's no stretching, then the ratio of the determinant of the second to the first fundamental forms is determined entirely by the metric. So this is if you want a restriction on isometries, conversely, in some circumstances, you can also show that if you can solve this equation, you can get an isometry from that. Okay? So this is really a necessary condition, and in circumstances that I'll use it's also a sufficient condition. If you have locally that the surface is given by a graph, then there's an expression for what this Gauss curvature is, this ratio of these determinants. It ends up being the determinant of the matrix of second derivatives divided by some factors that depend on the gradient. So this is the equation that we want to solve. And if k is negative, this is a hyperbolic Monge-Ampere equation. Of course, there isn't a theory for hyperbolic Monge-Ampere equations at the same level as there is for the elliptic case. And there are good reasons for that, some of which I'll talk about. So, the quest of saying, give me all solutions of this is perhaps too hard a task. And let's then think about, are there simpler versions? Is there a way to understand the geometry of these equations? And here is a simple idea from dynamical systems. So if you have a differential equation, y prime is f of xy, in the neighborhood of a point x naught, y naught, if this right-hand side is not 0, it's enough to solve the simple equation u prime equals 1. If it's not 0, you can really take it to be just a constant 1, because you can always construct a change of coordinates that reduces this equation to this equation. So it's a normal form for these equations away from bifurcation points. Of course, if this is 0, then you have to do more work. Okay? So what might be a normal form for this equation? And a normal form for this Monge-Ampere equation, if you want, or a local model, is I don't like all these things with the denominator. So in a way, it seems that, and we can make this precise, the key point here is in the highest order derivatives, and this is a fully nonlinear equation. So that is what we don't want to lose. So a local model for this, depending on the sign of k, is that the determinant of the matrix of second derivatives is plus or minus 1. And can we construct solutions? Yes, these are second derivatives. So if you take locally a quadratic function, the second derivatives are just numbers. So this reduces to just an algebraic equation. The determinant of q is plus or minus 1. And so there is some local change of coordinates that makes this equation look like one of these. And this is true. And in the elliptic case, you get regularity just from looking at this, if you want also, or you get nice behavior by analyzing solutions of determinant q is plus 1. Let's look at what happens in the hyperbolic case. So in the hyperbolic case, if you have a function that has 0 derivatives at x equals 0, y equals 0, so it's a homogeneous quadratic, the determinant of this is just ac minus b squared. So the fact that that's negative means this quadratic form can be factored into 2 linear forms over reals. So there's 2 real roots for this corresponding quadratic equation. And so your W locally is a product of 2 linear forms. And if you now look at lines, so if you set the equation that this first linear form is, say, a constant, say 2, then along that line, with respect to an affine parameter on that line, this factor, it's linearly independent from the first factor. So this is a linear function of the affine parameter along the line. X and y are themselves linear functions, and W, because this is a constant, is also a linear function of the affine parameter. So what this is saying is every solution to the hyperbolic case where the determinant is negative, with the restriction that it's locally quadratic, is a ruled surface. So there are two families of lines whose projections on the xy plane are given by these two linear forms being constant. So here is a model that's in our math department, and they actually sell these things on Etsy, apparently. I should get myself one. But so the solutions here are these quadratic surfaces that are doubly ruled. So what is my point to all of this? This is all pretty simple. It's the following, and it's based on the following. So let's record an observation. If you have a quadratic function, then the gradient is a linear function with the same matrix. So in particular, W itself will be 1/2 the gradient dot xy. So what do we know about these ruling directions? Yeah? So along the ruling directions, W is 0. Okay? So along these directions of the rulings, the gradient is orthogonal to the position. So if you think about these rulings and you project it down, you're going to get little parallelograms. And if you look at the gradient to the surface along these parallelograms, you have the following picture that in xy, you have a parallelogram, which we can take to be a rhombus. In the PQ plane, this line, this blue one, gets rotated by plus pi over 2. The red one gets rotated by minus pi over 2. And it's going to take these parallelograms and give you another set of parallelograms, or take these rhombi and give you another set of rhombi in the gradient plane. So at each point, we can define an angle from the xy projection, a dual angle from what happens from looking at the gradient of the surface, and the angle plus the dual angle is pi. Okay? So if you have, like in the pictures that I showed with the quadratic saddles, at each point, there are 4 of these rhombi that come together. These 4 angles add up to 2 pi, which means the 4 dual angles from this equation will also add up to 2 pi. That makes sense. Okay, so this is telling you something that it should be consistent. Yeah, if you have if you go once around and come back to this point, the normal vector will also make a circuit and come back. It'll go in the opposite direction, but it'll again come back to the same point. But, and here's the but, we have other, if you want, weak solutions to this problem. And this is based on this idea that these quadratic surfaces project down to give you these rhombi. So, you can take a quadratic saddle where you pick this number A so that the angle between these two lines is, so 2 pi is, so that pi is a multiple of this angle. So here I made these angles 60 degrees, which means I can have rhombi with angles 60 degrees, but 6 of them coming together at a point. And then you can fill in the rest of this. So here is now a grid or a network of rhombi, but this point is somehow special because it has 6 neighbors. Every other point has 4 neighbors. From the geometry that we just talked about, we can lift this to a solution to this equation. Determinant Hessian is -1. And if you lift this, you will get a surface. Again, each piece is piecewise quadratic. So you can think of this as each of this is one sector of a quadratic saddle, except the angle is 60 degrees. So you can put 6 such sectors together. Okay, so here you have 6 sectors coming together on this surface. This surface is clearly not smooth. Yeah? So because if you take the intersection of the tangent plane with this, it cannot be C2 because it's going to have 6 rays of intersection. So, and further, because 6 such rhombi are coming together, what would be the image of the normal map as you go around the circle? The angles in the dual plane will be 2 pi over 3, and 6 times 2 pi over 3 with a negative orientation will give you an angle of -4 pi. So this point here is a branch point for your normal map. And as you traverse a little circle around this in your domain, in the normal image, you will traverse not a simple closed curve, but a curve that winds around say the North Pole twice. So what we get from this, this is well known, and some of this goes back to work by Rosendahl in the 60s. The resulting surface is C11. So it's piecewise quadratic, but it's patched across these objects, which we can think of as lines of inflection. So the surface is curved this way. As you go through that line, it's curved the other way. Now, the seeming, non-smoothness here, it looks like there's a bend, is an artifact of my drawing these lines. The surface itself is C11. So it's not C2, but it's pretty close. But there's also a difference, or there's this extra feature, namely there's a point where it seems like we should be able to define an index, and that index is not what you would expect for C2 surface. Okay, and so this is true. So here are the quadratic saddle. If you draw the gradient and go around a circle, you see that if you go around the circle once, say clockwise, the gradient will go around counterclockwise. And here is the thing with a branch point where you put 8 quadratic pieces together, and now you get something else. Okay, so the key message in what we've done is that these branched isometries, they cannot be approximated by smooth isometries. Okay, so this thing cannot be approximated by C2 solutions of the same equation. And so in particular, this then leaves open the possibility that if there are functions which are continuous in whatever sense we are trying to approximate, I have to make that precise. There can be an energy gap for these functions. These have consequences for numerics and so on. So that's going to be the rest of my talk. We can build on this idea. Right? So what we can do is we can take a regular solution, so that's a quadratic, take out a sector, by which we mean a piece that's bounded by 2 of these straight lines that are defined by the quadratic, and then fill it in now with 3 sectors. Now what we've done here is we've introduced one of these points, again, where locally there are 6 patches, 6 quadratic patches in a neighborhood. And you can do this recursively. And so if you do this recursively, you start getting these shapes with more and more undulations as you move out. And that's exactly what we saw in these biological objects. So the question, in a way, is, will the system want to do this? Are there energetic benefits of doing this? And can this explain why we see these things in nature? Right. Any questions about anything so far? So the key point here, or the question that still remains is, whatever we did so far was for the very simple equation that the determinant of the Hessian is -1. But of course, the geometry of pseudospherical surfaces, that is not the right equation. It's just some kind of local model. So can we build from that to lift it to this full equation is kind of the question. And so it turns out the answer is yes, and for that we need to look at asymptotic lines of C2 surfaces. So an asymptotic direction at a point, one way of thinking about it is you take the tangent plane at that point and you intersect the surface. If your surface is C2, then locally it's a quadratic saddle, so there's got to be 4 rays at this intersection, and those give you your local asymptotic directions. With some assumptions on regularity, you can show that these directions are coherent, so you can actually find integral curves for these 2 sets of directions, and they give you your asymptotic curves of the surface. And this goes back to work by Hartmann and Wintner, and there's some really nice work by Dorfmeister and Stirling in the low differentiability setting. So what is how do we use this notion for the kinds of surfaces that we just developed? So you take a point P here, say it's this central point, and it's immersed in R3. TP is a tangent plane at P, also an object in R3. And you can define a number MP to be the number of components of taking a small ball about this point P in your surface and taking out TP from that. That's going to disconnect the surface. And if you have a C2 surface like the one in the previous page, you will get 4 components, but here you will get 6. Okay? So that defines a number MP. We want to show that this is related also to this topological kind of index, which had to do with the winding number of the normal. And so here is the idea. So there's a lot of words, but let me just point to this equation. So S1 is a circle. You can embed it in your surface. That's a small circle centered at P. The normal map will take this to the sphere. There's something to be shown, namely that your map is locally, it will avoid the value at P. So you can find a small enough circle that you will not get n at P again, and also avoid the value at minus n of P. So this punctured sphere is then retractable, but back down to the circle. So there is an index we can define for this object. Further, this index is related to the number of components by Jp is 1 minus n. So this object turns out to be nicer in terms of you can study properties of this degree and its stability under convergence in various senses. And because of this relation with MP, that also tells us something about our surface. So that's the basic idea. And so the theorem that we have here is the following. Okay? So in a way, this tells us that these branch points are robust, and they are an important property of the surface. Okay? So let omega be a domain in the hyperbolic plane, and you have a C11 immersion. Okay? The question is, can we approximate this by C2 immersions with constant negative curvature? And the sense in which we want to approximate is we want the energy that we define, the maximum, say, mean curvature, to be bounded. So this makes sense also in C11, right? Because if something is C11, then the first derivative is Lipschitz by Rademacher's theorem. It has almost everywhere curvature. We are asking that quantity be essentially bounded. So there's some essential bound on the curvatures, and the convergence, I could have taken W infinity. I can even do something weaker. I could do W22 log. If we have this notion, then this degree is stable under this convergence. So if you approximate by things which are C2, then for your limit immersion, your MP should be 2 at every point. So that means you don't get branch points. So 2MP again, like we said before, is the number of asymptotic rays that are incident upon P, and the degree of a branch point is an obstruction for approximation. So the ideas of the proof are, to use the thing from before of using the small circle, but the problem is that the size of the circle might depend on the immersion, so you need some kind of uniformity. So you want to show that there's a uniform size you can take to these circles, and that follows from some ideas due to Fritz-John and then in the theory of mappings with bounded linear distortion. I will not talk more about this, but the details are in the paper. Okay, so the upshot here is that this way of defining singularities or special points by looking at them as branch points for the Gauss normal map that is relevant in that it's preserved by the natural notion of convergence we need for the mechanical properties of the surface, and this separates out the class where you have non-trivial degrees or non-trivial branch points from the ones which are smooth. So any questions about any of that? Okay. So the second part is about assume that we do have these branch points. What can we say about them? And I'll just present a couple of results in this direction. So I want to set the context more generally. This is related to not just this particular problem, but also the study of Monge-Ampere, hyperbolic Monge-Ampere equations. So in the somewhat smooth setting, you have a Monge-Ampere equation. It's any equation of this form. And it has a discriminant that you can linearize about a solution and compute this object. Now, in general, you would expect that this quantity will depend on the solution, on the U. But if you expand this out and use the equation, there's this remarkable feature that what you end up with does not depend on any of the second derivatives of U. It just depends on the quantities A, B, C, D. And so the Monge-Ampere equations are special among the class of all fully nonlinear equations because they have this nice feature. Okay? So we can recast this as an exterior differential system. So this is the jet space, and it has natural contact form on it. So x, y are independent variables. U is your function. P and Q are the components of the gradient. And then on any solution, this form should pull back to 0. And the equation that we wrote down can be also expressed as a 2 form in these quantities P, Q, U, X, and Y. Okay? So a Monge-Ampere equation is given by this form theta and a form psi that's linearly independent from d theta. So the case that's hyperbolic corresponds to the following situation where, as before, there's some quadratic equation that has 2 real solutions. So there's 2 real factors, lambda plus minus, which depend on x, y, p, q, and so on, such that psi plus this lambda plus minus d theta can be factored. So with lambda plus, it gives you a pair c plus wedge eta plus, and with minus c minus wedge eta minus. These are now 1 forms, and these then give you can define. So because these are 1 forms, there's coordinates you can put on here. You think of them as asymptotic coordinates with respect to which all these quantities are given now by first order differential equation. So that's the nice geometry of hyperbolic Monge-Ampere equations. In the characteristic variables, you can write this equation as first order equations for all these quantities in terms of these characteristic variables. So let's see how that applies to our case of interest, namely surfaces with constant negative curvature. So U and V now are going to be these characteristic or asymptotic directions. And so there's the normal, the Gauss map is some mapping n of UV there. Okay? So if it's smooth enough, then of course you have these relations from the fact that the norm of this is 1. And so the idea here is to use the Frenet-Serre formula to write the derivatives of your immersion in U and V in terms of the other vectors in the problem. So the other vectors in the problem are the derivatives of this normal map with respect to U and also these things crossed with them. Okay? So these are the various objects. And it's a calculation, but you see that constant negative curvature means that the immersion, the U derivative of that is partial U of the normal map cross N. and this is minus partial cosine. So this connects with things we saw before, namely, we saw earlier that the characteristic curves were rotated when you took the gradient by an angle pi over 10. So this is saying that if you look in the plane that's orthogonal to the normal, that's exactly what's happening. The characteristic curves in the position or in the immersion are orthogonal to the characteristic curves in the normal image. Okay, so this is, if you want, globalizing the earlier argument with the determinant of the Hessian is -1 to this setting where your map is now into a sphere. So this thing, these equations go back to the 1800s, the Lalievre formulae. So, you know, to check that this actually works out, you can look at the ratio of the area of a little UV rectangle in the normal image, and that is, of course, minus from these equations the area of the image on the surface of the same image. Okay, so this is curvature equals -1. Okay? So you also get as a consequence that these are asymptotic directions. So what does this mean? This, what I'm saying, it seems, is like you take a map, any map, n is a function of u and v, and then you construct R by doing these two equations, and you've gotten yourself a pseudospherical immersion. Now, that cannot be right. That seems like there's too much freedom. This seems too easy. Yeah, so we are clearly missing something. So what is the point we're missing? And of course, it's clear from here that I cannot independently prescribe the u and v derivatives of some quantity. If I take the mixed derivatives, they have to be equal. And this is, of course, what gives you Gauss's equation and so on. So this is a useful idea, but there is an additional consistency condition. Okay? So what is this consistency condition? Okay? So again, these were the equations we had for the immersion given the normal map. If you take the v derivative of the first equation and the u derivative of the second and equate them, you get this compatibility condition. This is telling you that the map N is Lorentz harmonic. So if you start with any Lorentz harmonic map N, you can then construct your immersion by this pair of equations, and that then gives you a pseudospherical surface. Okay. So this is, of course, very much like the wave equation, and there's a discretized form for this. So there's a nice discrete differential geometry that's based starting from this point. We use it in our work, but I'm not going to get to talk more about it. The point I want to make is, being a wave equation, if you prescribe data along, say, the line u equals 0 and along the line v equals 0, this is characteristic data for the wave equation. So it's a Gauss problem. Long as they're consistent here, you can then solve the wave equation by integrating this thing along each of these little quads. So if 3 points are known, that determines the fourth. And likewise, once you know this, you can determine this point and this point and this point. So that's the way in which we can use these equations to construct explicit pseudospherical immersion. Okay? You note that these equations are invariant under changes of coordinates. So if you take any one-to-one mapping that's differentiable, they will have the same form. So your u and v are not uniquely determined, rather they should have this kind of freedom. And so the objects with these kinds of freedom are Lorentz surfaces. So let me just say a few words about them. So a Lorentz surface is a surface with an indefinite metric, actually with a conformally equivalent class of indefinite metrics. So this tells you that for a Lorentz surface, there are local directions, which are null directions, but there aren't preferred null coordinates, which again agrees with our picture that there should be these directions, but any one-to-one differentiable mapping of it should give you the same notion. Okay? So on a Riemann surface, there's a well-defined notion of angles between tangent vectors, not their size, or equivalently the local notion of a round ball. On a Lorentz surface, there's a well-defined notion of causality. So you can define whether vectors are space-like or time-like, but not really a notion of length. Okay? So if a surface is a C11 immersed hyperbolic surface, then the equivalence class, you can think of this as a surface where you give it a metric given by the second fundamental. Then that defines an Lorentz surface, and this Lorentz surface then captures everything you want to know about the geometry of the characteristics. Okay, so I can see that I'm running short on time, so I'm not going to get to everything, unfortunately. But let me maybe talk for another 4 minutes and then stop and see if there are questions, and then we can have a discussion. Does that sound okay, Armin? Okay, good.
Yes, that's fine.
Yeah. So given an immersion, we can construct these characteristic curves by intersecting with local tangent planes. We can also go in the other direction, okay? And that's the interesting direction, that you can start with a network with the following properties. It's a quad graph, which means it's a cell decomposition in which all the faces are quadrilaterals, and at every point there should be an even number of quadrilaterals. In that case, there's a consistent way of defining what we mean by U and V, or equivalently, there's a consistent way of defining time-like and space-like. Okay? So, if you think about it, you think, say, this first rhombus is space-like, the next one is time-like, space-like, time-like, space-like, time-like. To be consistent, we need an even number at every point. So that is the structure of the characteristic directions. And given this structure, we can then solve the Lelièvre equations to actually construct surfaces. Okay? So this is an example. So if you start with this quad graph, you get a solution to you get a pseudospherical immersion that's C11, and the fact that it's C11 is reflected by the fact that the corresponding quad graph has non-trivial connectivity. If you start with something that looks like this, you get this. If you start with something that looks like this, you get this flower. So we should think of these pseudospherical immersions in the class C11 as having two pieces of data. One is a topological skeleton, which is this object. And just like the intrinsic geometry of surfaces can be uniformized so that you have just a few classes of objects that represent all of them, this is now an uniformization for the extrinsic geometry. So the information in the actual extrinsic geometry of these C11 surfaces, in particular, the branch points and where they're located, they're all encoded in this graph. And then you get to prescribe different kinds of data and solve wave equations on each of these domains. And that's then the corresponding geometric data. And so that's the picture that we have. We can extend the Sine-Gordon equation to the setting. The Sine-Gordon equation, phi uv is sine phi, is for smooth pseudospherical immersions. If we allow for these branch points, it turns out, so here's the actual theorem. So if you have a branch point, you can construct these kinds of curves, which are now consisting entirely of U and V asymptotic curves. And then on the regular plane, such a closed curve will only have 4 vertices. You go UV, UV, you come back. Whereas if you have branch points, you can have more. And then if you integrate, there's an integrated form of the Sine-Gordon equation on these objects, which if you look at the differential equation, it tells you essentially that you get the sine phi, but you also get a contribution from each of the branch points, and these contributions are all of the same sign. So maybe that's a good place to stop. I can, yeah. So I didn't get to talk about the conjecture and then proof of it, but that'll take far too long. So let me stop here and see if there are questions, and then.
All right, thank you very much.
Thank you.
Ah, that's pretty good.
Thanks.